Hi, this is Ariana Shetty, and these are my results and procedures for Lab 1, which involves studying the interactions of charged tapes. When objects are moved around in different directions, rubbed together, or pulled apart, they have the capability to acquire either a net positive or net negative charge. With this lab, we will be focusing on adding excess charge to an everyday object, such as a piece of clear tape. We will also be utilizing a computational model to digitally visualize our results. Some fundamental principles shown in this lab include the electrostatic interactions between molecules, which deals with calculating the electric field and electric force produced by a charged object, the forces that remain in static equilibrium, and maintaining conservation of charge. So how was the main charged piece of tape, or U-tape, created? When two pieces of tape come into contact with each other and they're separated, it leaves one tape with an excess amount of electrons and the other with a deficiency of electrons. Some assumptions made for this experiment include assuming that the U-tape acts like a point charge and that all the U-tapes created have the same exact charge. We can also assume that the atoms on the tape are tightly packed into squares. I then began by observing the interactions of the charged tape with other molecules. When the U-tape was placed near my hand, I saw that the U-tape was attracted to it, indicating that they were either opposing charges or my hand was considered neutral. When the U-tape was placed near the negatively charged pen, they were shown to attract one another, indicating that the U-tape was positively charged. When two U-tapes are placed near each other, they will repel as they have similar charges. Lastly, when the charged U-tape was placed near the neutral book, they were shown to attract to each other. This is because both positive and negatively charged objects maintain a slight discrepancy in charge in comparison to a neutral object, therefore, they develop an attraction to one another. When setting up the experiment, I started by placing two books a certain distance apart, which secured the upper U-tape. I then held the lower U-tape, bringing it closer and closer until they began to repel, and the upper tape rose above its original position. The distance between the two tapes when they repel was recorded and labeled as R, which will be shown in the data measurement section. The forces that act upon the upper tape are the electric force from the lower tape and the force of gravity acting downwards on the tape. The first piece of data collected was the length of the piece of tape, which was an average value derived after multiple trials. We were able to then determine the mass of the piece of tape based on the length. And as previously stated, the distance between the two charged tapes, known as R, was recorded as well. The gravitational force utilizes the equation mass times gravity, giving us this value shown. We know that the sum of the forces in the y direction for the upper tape was 0, which means that the gravitational force is equal to the electric force, giving us that same value of 2.256 times 10 to the negative third newtons. We can then plug that value into the electric force equation to derive the charge of the floating piece of tape. That number is then plugged in and divided by the standard charge of an electron, giving us the total number of electrons, which means tape B has a deficiency of 1.59 times 10 to the 11th electrons. I'm going to go ahead and give a quick rundown of some of the most important parts of the computational model code so you can gain an understanding of the thought process behind it. I started by creating the two pieces of tape as point charges, hence labeling them as spheres. I then applied the electric field function from Lab 0 to help derive electric field values for both the point charges. I then calculated the force of gravity, aka the electric force, to solve for the charge of the upper tape, or tape B. The electric field was then solved for using that function. And in lines 45 through 50, I solved for the number of deficient electrons on the tape, as well as the ratio of atoms that gave up electrons when the U-tape was charged. The computational model charge assigned to the upper U-tape is consistent to the value I derived throughout the equations, which was shown to be 2.55 times 10 to the negative 8th coulombs. We can also determine that there is a minuscule percentage of atoms that gave up electrons when the U-tape was charged. So we were asked two questions in relation to our lab. The first asking if electrons and protons switch charges, what would happen? I stated that the varying attractions of the tape with other objects would still remain the same because the opposing charges would attract and the same charges would repel. The second question stressed the importance of handling the tape as little as possible because when your neutral charged hands touch the charged tapes, the tape transfers charge onto your hands. This would be considered a major source of error as the tape will have a slightly different charge every time it's handled, leading to discrepancies as you continue throughout the experiment. In conclusion, I learned about the aspects of electric force and electric field by applying them to an everyday object such as a piece of tape. I was also able to apply the principle that forces remain in static equilibrium, which is shown when the upper tape remained fixed at a certain distance from the lower tape. Conservation of charge was seen when the U-tapes were created, as no charge was lost. There was only a transfer of electrons between the base tape and U-tape. Thank you.